Yeah, around 4730, he's talking about theorem proving using machines, and he talks about normal form proofs. A normal form proof for somebody who's used to pi calculus or something, or lambda calculus. You know what a normal form is, and if you translate your lambda notation into combinatorial logic using SK combinators or something, then you know what normal form proofs in, well, it's called weak normal form, but they're still normal forms in combinatory logic. Broadly in mathematical terms, and you think about all those proofs that students have to do, it's quite tedious. Once you define a few theorems of set theory, you then have and you have some kind of proof system. It doesn't need to be formal, it can just be paper proofs. These are in my my notes to Glyn Winscoll's Discrete Maths 2 course. There are then dozens and dozens of useful little formulas. They're all pretty much all equivalences that you prove, and the process by which you do those is pretty much constructing some kind of statement using the definitions of the objects that your theorem speaks. So, for example, you're proving that, now I've got to actually try and remember these damn things. There's this duality between set theory and logic. So, when you're proving theorems about intersections and unions of sets and their equivalences, there's a one-to-one correspondence between logical equivalences like De Morgan's laws. Something like A and B or C, in brackets, is the same as A or B and A or C. So in other words, you can push in disjunction and conjunction. You can push them through the brackets and distribute them over the terms within the brackets if you swap conjunction and disjunction within the brackets. And there are similar versions for, or do you have to take the complements as well? I can't remember. I seem to remember there's something about negating when you push the terms through into the brackets. But that's speaking in logical terms. When you treat it as a proof in set theory, there's a subtly different way of thinking about things. You're taking, for all sets X and all sets Y, and doing this stuff with them, you invariably end up unwinding definitions, which is expanding them, saying what a union means, so that the union of two sets means that for all sets A, B, X is an element of A union B if and only if X is an element of A and X is an element of B. So that's unwinding the definition of union. So when you're proving one of these equivalences, you're unwinding these definitions, and then you're somehow winding them up again in another. Oh, I'm lucky a car didn't come around when I was there. That's water, does not smell nice. That's from the toilet. It's going into the lake. I remember in Cochabamba, there was a block of flats that used to empty their latrines. They had a filter system. They could produce clean water, crystalline water, but full of all the aromatic compounds, shall we say, of sewage. And this fucking stuff was drained out overnight illegally into the street and produced a huge puddle. And some bastard saw me, and I was pretty well known, and he drove his car, he accelerated, and he cut in on this puddle, and I was head to toe washed in shit water. Boy, I was angry. Anyway, back to theorem proving. I think now, as far as normalization goes, the procedure of kind of running some kind of redox lambda-like reduction process, like normal order reduction, is slightly more complicated, because you need something like Nuss-Bendix's completion to be able to turn your set of rewrite rules into convergent rewrites. But so that's an example of what he means. I think that's how I take what I take him to mean when he says these proofs that the computer would produce would be a kind of normal form proof. And there is something holistic about a normal form proof. And he says, whereas the kind of proofs that a mathematician comes up with are not of that nature, that mathematicians tend to invent new concepts, new objects, new denotations of their discourse. And so advances in mathematics are often because of new ways of expressing equivalences. But exactly how you define them as being equivalences is pretty important. And so I had this discussion with Daniel Tubenauer about the clever definitions, the real advances in mathematics, and the creative spark in mathematics tends to come from clever definitions, or in some sense beautiful definitions. And my canonical example is the definition of a tiling in the book Grunbaum and Shepherd. You read it and it's not obvious, but it allows you to say a lot about tilings. It's a lovely definition. I can't even remember what it is. It's to do with the vertices, and it's to do with he defines vertices and edges. Maybe it is a graph theoretical thing. I miss Daniel's. He's incredibly disciplined. He does three or four uploads every Saturday. and I haven't looked at them for at least 2 weeks. So there we go.